Hi and welcome back to my channel. This is my second video I'm filming today, and I realized after I stopped recording on my last video, the first video I posted, my face was down in the left corner, so it was blocking most of what I was trying to explain on the COMSOL interface. So I've moved it up here, and yeah, so now you should be able to see everything I'm doing. And hopefully this one turns out better. So today I'm going to be doing the COMSOL tutorial for laser heating of a silicon wafer. And I thought this one was interesting because my last job was in semiconductors working at a fab, so this was very relevant to that job. I just want to make sure this is displaying right. Yep. Looks like it's recording. Okay, so this laser annealing is something that's commonly done in semiconductors. So that's kind of what this example is about. I believe it doesn't specifically say, it just says it's a silicon wafer heated up by a laser that moves radially in and out over time while the wafer itself rotates on its stage. So basically you've got a laser, and then the silicon wafer is on a stage and it's rotating while the laser goes back and forth, so it eventually covers the entire wafer. And the dimensions of this wafer in the example is 2-inch. It's very small. Most fabs are like 6-inch, and now moving to 8-inch and 12-inch even at places like Intel. But we've got a 2-inch silicon wafer heated for 1 minute by a 10-watt laser that moves back and forth while the wafer rotates on its stage. Assuming good thermal insulation from the environment, the only source of heat loss is from the top surface via radiation to the processing chamber walls, which are assumed to be at a fixed temperature of 20 C. The laser beam heat source is modeled as heat source moving across the surface of the spinning wafer. To model the rotation of the wafer, we're using the rotating domain feature. And again, all the examples I'm going to be doing are only using COMSOL multiphysics because that's the only package I have. I don't have the additional modules. And we'll use the waveform function and set variables to define the Gaussian distribution of laser heat load around the focal point as it moves back and forth across the spinning structure. So here's the results we're going to generate for temperature versus time, and Tmax to Tmin and Kelvin versus time across the wafer, and then we'll have a surface plot of the temperature. Alright, so to get started, we'll open COMSOL. I'm using COMSOL 6.0. This is the most current version right now at time of filming. So we're going to do new file, model wizard, 3D model. So last time we did a 2D model that was asymmetric. This time we're using the 3D model. And then we're selecting heat transfer in solids, HT. So expand that one, heat transfer in solids, HT, add, study. And in the select study tree, select general studies, time dependent. So there's time dependent selected and done. Now, first thing we do is, once it appears, there we go, fill in our parameter global definition. So in the model builder window under global definitions, let me just expand this a little bit and make this one a little smaller. Okay, so here's global definitions, parameters 1. We're going to fill in these from the table provided. So the radius of the wafer we'll call r_wafer expression 1, and then the units in brackets and you'll see in the value, whatever units you put in, it will convert them to the standard SI units that are used in the COMSOL equation. So it converted your inches to meters, wafer radius. Next, we have the thickness of the wafer, which we'll call thickness, 275 micron. That is a very thin wafer. I think the wafers we used at the fab I was in were nominal thickness ranging from like 625 to 675, and anything thinner than like 500 microns was considered thin. So 275 micron wafer is extremely thin. And this is the rotational speed, 10 RPM. If you want to speed through this part, I should start adding chapters to my videos so you can skip through to different parts, like parameter input, geometry modeling, boundary selection, stuff like that. Okay, so we just put time for laser to move back and forth is 20 seconds. R underscore spot is going to be the laser beam radius of 2 millimeters. Laser beam radius. Emissivity is 0.8. Surface emissivity. So I'd have to look up the definition of emissivity, but I think like the emissivity of a perfect black body is 1, which is basically like an object's ability to radiate, I'm pretty sure. Don't quote me on that. And then the laser power is 10 watts. Okay, so here's our, I'm gonna go ahead and save this as, what's this problem? Laser heating of a silicon wafer. So I'll call this laser heating silicon. All right, so that was our global definitions. Now we're moving to geometry. And the geometry toolbar, click component 1, or click cylinder. So here's the geometry toolbar. I'm going to click cylinder, and then under size and shape and radius, we'll type in R underscore wafer, which was the variable we defined for the radius. And in the height, type thickness. So the height of the wafer is just the thickness of the wafer. And then block 1 in the geometry toolbar, click block. So now we're adding a component, and you can see the cylinder already appeared. We didn't even have to click build selected, but I guess it automatically does that when you add a new component. And then in the radius, now we're on to block. In the settings for block, locate size and shape, and in the width, type 2 times radius wafer, 2 times R underscore wafer. So this is what I was kind of referring to in my last tutorial, how you can define one variable and then use that for scaling in different components. So our cylinder and our block both use the global definition of radius wafer, which we could change, and it will keep the scaling of the wafer the same. And the depth, we just did depth, width and depth are both 2 times radius wafer, because it's a circle, and then the height is thickness. All right, locate the position section, and the X field, type negative 0.95 X, or 0.95 times R wafer. So we're starting the geometry for this block at X equals negative 0.95 times the radius of the wafer. And then the Y field, type negative R wafer. So the Y coordinate of the corner is at that Y coordinate. Okay, and now at the intersection, which we're going to add to intersect the cylinder and block 1, we go to Geometry Toolbar, Booleans and Partitions, Intersection, and in the graphics window, press Ctrl A to select all the shapes. Okay, so they're all selected, which you can tell because they're purple. And in the settings for the intersection, click Build All Objects. So build all objects, and you can see what we did here is create a square. So if I click undo, we want the shape to be like this because that's how a silicon wafer in the fab will have a flat end. So you'll call this in the crown and this in the flat. And these are, the wafers are created, well, first you create a silicon ingot or a boule, which is basically a seeded, you seed a crystal and then grow an ingot. So it grows radially, and you have the super long tube or boule, a long boule of silicon, and then you put it on its side and slice them 275 microns thick. Well, it would be thicker than that because then they're going to get polished on one or both sides. And then it'll have a flat end, which is typically how you orient it upward in a cassette for processing through the fab. So to make this shape, you have to make a circle, overlay the square, and the if we go to the block, the corner position of the square is how we'll position this so the flat is intersecting with the circle. And then when you create the intersection, so if we look at the Booleans and partitions, you can have a union, intersection, or difference. And the little icon sort of gives you an inclination about when to use each of those. Union is combining the shapes. Intersection means you delete anything that isn't overlapping. And difference is you only keep the part that isn't overlapping. So when we did the difference, we're left with the circle minus this tiny section, leaving a flat end. Okay, so now on to definitions. Variables 1. So in the model builder window under component 1, right click definition and choose variables. So component 1, under component right click definitions. So right click definitions and choose variables. And the settings window for variables, locate the variables section, and then we're entering these settings. So just like the global definitions, we're going to enter the name of the variable, the expression, which is actually either the numerical value or, in this case, how you calculate it from provided values. Okay, so when you see this in yellow, it means it's using a function or operator we haven't defined yet. So let's see, did I miss something in the global definitions, or maybe we'll define it in a little bit. Yeah, so it's missing something right now, but I'm sure it will come later in the tutorial. So the description is the X location of the laser focal point. Y focus is the next one. Y underscore focus is 0 meters. So let's just copy this one. And then that's Y. And then R focus underscore focus is the distance from the focal point. So we'll do the square root x minus x focus squared plus y minus y underscore focus squared. Oh. And we have 2 end parentheses times exponent negative 2 times r focus squared over r spot squared. And I probably missed an end parentheses somewhere. Let's see. Go through it from the beginning. Okay. Oh, I started writing the flux equation because I'm going back and forth. So it ended at y focus squared okay, there we go. And then for the last variable, flux, this is going to be P 2 times P laser over pi times r underscore spot squared times exponent, and that's the rest of what I had here. Okay, that looks right. Nope, I'm missing another. Let's see. 2 times P laser over pi times r spot squared. Now I have 2 in parentheses times exponent negative 2 times r focus squared over r spot squared. Oh, right here. Okay, and then the name or description of these: distance from focal point and laser heat flux Gaussian. Alright, so there's our variables for component 1. We've got the laser focal point in the x and y locations, coordinates, and then the distance radially from the focal point, and then the laser heat flux from the focal point. Next, we're going to be working on the waveform. So in the home toolbar, click functions, home, functions, and select or choose local waveform. So in the local group of this drop down, we'll select waveform. In the settings window for waveform, type triangle in the function name. So here's our function name. I'm going to overwrite the WV1, and this is where the function that we called we just referenced it in the variables we entered a second ago, and it was yellow because we hadn't created it yet. So now we're creating the triangle function that it will call. Locate the parameters section. From the type list, choose triangle. So now pick triangle under parameters. Clear the smoothing. So we don't want smoothing. In the period field, type 1. So instead of 2 pi, we're going to put 1 period. In the phase text field, type pi over 2 radians, and click plot. Okay, so here's the plot it produced, and now we're going to maximum. In the definitions toolbar, click probes. So we'll go to the definitions tab, probes, choose domain probe. In the settings window for domain probe, type maximum in the label field. In the variable name text field, type tmax, T_max, so temperature maximum. And from the type list, choose maximum. So we'll change the probe type from average to maximum. Now we're going to create one for average. In the definitions toolbar, click probes and domain probe once again. And now we're going to add one for average. So we'll do the same thing as we did for max, labeling it average. T average is the variable name. Type is average, so we don't have to change that. And then we're going to add one for minimum. Minimum variable is tmin, and type is minimum. All right, and now we're moving on to global variable probe 1. On the definitions toolbar, click probes, global variable probe, and in the settings window for global variable probe, type tdiff in the variable name. Oh, what are we calling the label here? Okay, undo. Let's just add it again. Probes, global variable probe. So we leave the label as the default, and we're just going to call the variable tdiff. Okay, and locate the expression section in the expression text field, type tmax minus tmin. Tmax minus tmin, so we're just creating a difference of the two probes we created, max and minimum temperature. In the definitions toolbar, click moving mesh. Let's see, here's moving mesh, and choose domains, rotating domain. Okay, because our wafer is rotating, so that makes sense. In the settings window for rotating domain, locate the domain selection. And we're going to select all domains. So instead of manual, we'll just choose all domains. In this case, there is only one, so it didn't really make a difference. Locate the rotation section here. And from rotation type, choose specified rotational velocity. So we're changing from user defined. You can choose from rigid body, specified rotational velocity, which is what we're going with. And from rotational velocity expression, choose constant revolutions per time. So we're changing from constant angular velocity to constant RPMs. In the F text field, type V rotation. So this was the variable we set in global definitions as our RPMs. V rotation. And then we're leaving the initial angle at 0 radians. Heat transfer in solids. So now we're moving on to setting up the physics. Include the wafer's rotational velocity in the governing heat transfer equation. Next, add heat flux and surface to ambient radiation on the wafer's top surface. Heat flux 1. In the model builder window under component 1, right click heat transfer in solids and choose heat flux. So when you right click on the physics that we added when we were first setting up the model, this includes all these preset things you can choose from. So there's, we're choosing heat flux, but there's temperature, thermal insulation, symmetry, periodic condition. Let's see, we have flow conditions, heat sources. So for this problem, this is the one that's applicable, and also under, we'll probably be adding some of these for initial boundary or initial time conditions. Boundary conditions or initial values. So what are we picking? Heat flux here. Select boundary 4 only. So it looks like this is boundary 4, the top of the wafer, because that's the only surface that's radiating heat as per the introduction at the beginning. In the settings window for heat flux, locate the heat flux section. Okay, so here, and from the emissivity, I think I skipped a line here. Surface, in the settings window, for surface to ambient radiation, did I skip something? Oh yeah, I did. Okay, in the Q naught field, type emissivity times flux. So we're in the flux type. I didn't say to change this. In the settings for heat flux, locate the heat flux section. Yeah, so we're leaving the flux type as the default general inward heat flux, but if you wanted to change it for your particular model or problem, you could use convective heat flux or heat rate. So it just depends on, I guess, what parameters you have given, or what parameters are known for the problem. So we have the emissivity of the wafer and the rate of flux. So the model will calculate Q naught in watts per meter squared, which is what? Let's see, watts is a unit of power per area. So anything, a flux is an area per time. So, or something per area per time. So we have something per area. Okay, power per area. Now we're moving on to surface to ambient radiation 1. In the physics toolbar, click boundaries. Let's see, physics toolbar at the top, click boundaries, and choose surface to ambient radiation. And then from this section, from the emissivity list, choose user defined. So you can either define a material you're using. So another way to do this might have been to just select the material as silicon and then use the emissivity for material. But in this case, we actually defined it as a parameter in the global definition. So that's what we're doing here. Emissivity was the variable name. And then we're adding a material. Oh, we are adding a material. Okay. So I guess they just wanted a very specific emissivity we entered rather than use the material. So in the home toolbar, click add material. Where is it? Here we go. Add material. It looks like a little honeycomb icon. And then it opens the add material bar on the side, or dialog box on the side here. So you can type in a material you want to search for. And if I type in silicon, we get polysilicon or silicon. Okay, so click add to component in the window toolbar. Oh, I added it twice. Delete one of those. Okay, so now you see silicon appears under materials for component 1. So I'm going to X out of this window. And in the home toolbar, oh, it's just saying to close. You can either close the window by clicking this in the toolbar or just Xing out of it like I did. So mesh, now we're on to mesh definition. Use a fine triangular swept mesh. So in the mesh toolbar, we'll select that tab up top, click swept. So that's the icon with 3 triangles. And in the settings window for swept, click to expand the sweep method section. So we'll expand sweep method, and from the face meshing method list, choose triangular generate prisms. Face meshing, so we're changing it from quadrilateral generate hexahedra to triangular generate prisms. Distribution 1, right click swept 1 and choose distribution. So if we right click under the model builder now, I'm right clicking in this listing and choose distribution. In the settings window for distribution, locate the distribution section and the number of elements text field type 1. So instead of 5 elements, we're changing it to 1. Why did it have 5 before? I'm not sure where the 5 came from as the default, but it said to change it to 1. And now in the size, in the model builder window under component 1, mesh 1, click size. So it's this first listing under the mesh 1 drop down. And we are using fine for this. All right, and build all. So it fills in our fine mesh in the triangular swept geometry. Okay, so now on to the time-dependent study. In the model builder window under study 1, click step 1, time-dependent. Oh, and then real quick, I just wanted to see, if you flip the wafer over, you can see the mesh on all sides. I mean, you can't really see it in the thickness because it's so thin, but you can see even on the sides, the mesh goes through. Okay, and then to go back to the full view, you hit the zoom extents button. And I don't really like that angle, so you can also use the go to default view, which is this red, blue, and green orthogonal axis called go to default view. And it'll change back to this. Okay, so in the model, going under study 1, click step 1, time dependent. Okay, so now we're going under time dependent, study settings, step 1, these actually don't have steps here. In the model builder window under study 1, click step 1, time dependent. Oh, there's only one step, that's why. It is step 1, time dependent. In the settings window for time dependent, locate the study settings in the output times text field type range. So we're changing the range from a start time of 0. It was going from 0 to 60 in steps of 1. So we'll change our step to 1. 60, you can also click on this if that's easier. And tighten the relative tolerance to better capture the effect of the moving heat load. From the tolerance list, choose user controlled. So we're changing from physics controlled to user controlled. It will usually default to physics controlled where that's available. And we're reducing this from 0.01 to 1e negative 3. So we're just making the when it iterates to, like, it won't stop on the solution until the relative tolerance has been met. So when you decrease the relative tolerance, you're saying, I want it to solve longer so it's more accurate. I want it to, it will take longer. You're saying you want it to be more accurate, but it will iterate more times until it reaches that tolerance, relative tolerance. In the home toolbar, click compute. So then we go back up here. Oh, right here is the compute button up in the upper left-hand corner. Okay, so then we just sit and wait while it's computing the results. It shouldn't take too long since it's a pretty simple geometry. And next we'll look at the results and study the spatial, change the frame to spatial in order to visualize the wafer displacement. Expand results datasets, click on the solution, and then we'll change the frame to spatial. We get a temperature surface plot for the wafer surface. And then we'll look at the max temperature, average, and minimum. And that's it. Okay, so in the next steps, we're just going to be generating these plots that were contained in the write-up in the first part. So figure 2, maximum, minimum, and average temperature of the wafer as a function of time, plotted against each other. Figure 3, difference between maximum and minimum temperatures on the wafer with time. And figure 4, temperature variation across the wafer. So it's interesting that this part of the wafer is much hotter. The crown is much hotter, so I wonder why that is. We've got the temperature scale here going from dark purple is about 520 degrees Celsius. I know this is in Kelvin. To 620 roughly Kelvin. So that's a pretty big temperature gradient, and I wouldn't have expected it to be at the crown. If your laser is going back and forth, I would expect it to be either in the center or around the edge. Okay, so it's done computing, and we get this pretty color gradient picture. And you can also change the colors. If it matters to you, you can go into the, let's see, where is it? You can change the title here to a custom title. I'll leave it at automatic. I'm looking for the color. Oh, from theme, color you can change to, oh, that's for the title. I don't want to change the title. How do you change the color legend? Here we go. Text, position. No, that's not what I want to do. This is the geometry. Plot dataset edges. Oh, this is for the geometry edges of the contour plot. So let's leave that at from theme. well, I can't remember how to do it, but I'll come across it later, I'm sure. So for the results, change the frame. Let's see. Okay, in the Model Builder window, expand the Results Datasets node, and then click Study 1, Solution 1. So we're under the Results drop down here, click Study 1, Solution 1. In the Settings window for Solution, locate the Solution section. Oh, it already has, so you can either choose Probe Solution 2 or the Study 1, Solution 1 for the data. And then in the Settings window for Solution, locate Solution section. Oh, I had the wrong thing selected. Okay, so under Results, expand the Datasets tab and then select Study 1, Solution 1. And in the Solution section, we are choosing Spatial from the frame list. So it's already selected. You can also choose Mesh, Geometry, Material, or Spatial. Okay, and then for the temperature default plot, in the Model Builder window under Results, click Temperature. In the Settings window for 3D Plot Group, locate the plot settings. So then we're going down to this section, and from the frame list, choose Spatial. So we're changing from Material to Spatial. In the Temperature HT toolbar, click Plot. So up here, we have the temperature tab opened, and we're going to click Plot. Click the Zoom Extents button in the Graphics toolbar. So it's already showing that view. And compare the temperature variation with that shown in Figure 4. So this is the same figure we looked at before in the COMSOL document. All right, now we're going to create the isothermal contour plot, which shows the temperature isosurfaces. So in the Model Builder window, click Probe Plot Group 3. Here's Probe Plot Group 3. Okay, so we already have a plot of the max temperature in dark blue, the average temperature in green, and the minimum temperature in red. And then in light blue at the bottom, we have the delta from max to min. Okay, so in the Settings window for 1D Plot Group, locate the Legend section. For the position list, choose upper left. So down Legend, we can change the position from upper right to upper left, just so it's not blocking that quadrant of the graph. In the Model Builder window, expand the Probe Plot Group 3 node, then click Probe Table Graph 1. So expand Probe Plot Group 3 right here, and select this one. In the Settings window for Table Graph, locate the Data section. In the Columns list, choose Temperature. So columns, we've got Temperature Maximum, Temperature Average, Temperature Minimum, so we don't want to plot Tmax minus Tmin. And then we'll click Plot. So it just removed the delta in light blue at the bottom. And now we're going to create another one, Probe Plot Group 4, by adding a plot group. So from the Home tab, add plot group, 1D plot group. In the Settings window for plot, 1D plot group type, Probe Plot Group 4. in the label field, right click and choose table graph. In the settings window, look at the data section, and from the plot columns list, choose manual. Plot columns, manual. And I guess this is where we're plotting, yeah. So we'll put the delta in this one. So now it's on its own graph, or its own plot, separate from the max, min, and average. Okay, so that's it. How long has this been? That is the end of the tutorial for laser heating of a silicon wafer. So thank you for watching, and I'm probably not going to edit this one either, but at some point I will start putting more effort into these. I'm just really trying to get in the habit of making these tutorials and putting something out instead of overthinking it and not doing anything. So I hope you liked it. If you did, please leave a like, a comment, and subscribe for more COMSOL tutorials. Bye!